An object of mass m is attached to the end of a massless rod of length L. The other end of the rod is attached to a frictionless pivot. The object is raised so that its height is 0.8 L above the pivot, as shown in the figure here. After the object is released from rest, what are the tensions in the rod when it is horizontal and at the bottom? So let's start by drawing a free body diagram. And this is when the object is horizontal. So the object is going to be horizontal. So it's when it's over here. And the only force acting on it towards the center of the circle in the radial direction is the tension at the horizontal. And of course, the only other force is the force of gravity, or the object's weight acting downwards. And these are the only two forces, since there is no friction at all. So from this, if you remember Newton's second law, it says that the summation of all of the forces, or the net force acting on an object, is equal to its mass times its acceleration. So we can write it for the radial direction, that the tension at the horizontal position is equal to the object's mass times its centripetal acceleration, or radial acceleration towards the center of the circle. And this acceleration is necessary to keep it moving in this circle. And the centripetal acceleration, or radial acceleration, is given by mv squared over r. And in this case, r is simply the length of the massless rod. So it has a length L. And so our tension at the horizontal position is equal to the mass times the velocity squared divided by L. But we still don't know what its velocity is at the horizontal position. So we can solve for that using energy conservation. So we know that the kinetic energy at the horizontal is going to be equal to the gravitational potential energy that it once had. And the kinetic energy is given by 1/2 mv squared. And the gravitational potential energy is given by mgh, where h is the height that it was released from. And note that this is only true if you don't lose any energy to sources like friction or air resistance, which get dissipated as heat. But we're only assuming that energy is conserved and nothing is lost to heat. So the masses cancel, and the height is equal to 0.8 L, since it was dropped at a height 0.8 L above the pivot. So this becomes 1/2 v squared is equal to 0.8 GL. So v squared is equal to 1.6 GL. And note that we actually don't need to square root this, because in our equation, it's asking for mv squared, and we need to figure out what v squared is. So v squared is equal to 1.6 GL. And we can plug that back in. So the tension at the horizontal position is equal to the object's mass, or rather it's equal to 1.6 times the object's mass times the gravitational acceleration times the massless rod's length L divided by L. The L's cancel, and you're left with the tension at the horizontal is equal to 1.6 mg. So the tension on the horizontal is basically 1.6 times the object's weight, the mass's weight. So that's our first part. The tension at the horizontal is equal to 1.6 mg. Now that's the first part of the question, but the second part of the question asks us for the tension in the rod when it is at the bottom. So at the bottom, again, there are only two forces, and that is the tension force at the bottom and the mass's weight, or mg, the force of gravity. This is the diagram at the bottom. So again, we can use Newton's second law to help solve this. But now both of the forces are acting in the radial direction. So if we say that the radial direction is positive and this way is negative, that's towards the center of the circle, which is represented by the unit vector r hat. And so the tension at the bottom minus the force of gravity, again because gravity is pointing downwards in our reference system here, that is equal to the mass times the radial or centripetal acceleration, which is equal to mv squared over L, where L is the radius. So the tension at the bottom is equal to mv squared over L plus mg, or m times v squared over L plus g, where we simply factor out the mass. And again, we need to figure out what v squared is. So using the same principle from before of energy conservation, the kinetic energy at the bottom is equal to the gravitational potential energy that it had, which again is 1/2 mv squared. That's kinetic energy, and the gravitational potential energy is mgh. And this time, the height is equal to L plus 0.8 L, which gives us 1.8 L. This is because originally it starts at a height 0.L above the pivot, but once it goes to the bottom, it goes an additional distance L. It falls down another distance L, because L is kind of basically the radius of the circle that is traveling. So it will need to fall down this distance here, including the 0.8 L that it originally had. Its original height of 0.8 L. So again, masses cancel. So 1/2 v squared is equal to 1.8 GL. So v squared is equal to 3.6 GL. Again, we don't need to square root anything because the question is asking for v squared. So if v squared is equal to 3.6 GL, then we can plug that back into our original equation. So the tension at the bottom is equal to mass times 3.6 GL over L plus G. So again, the L's cancel. Tension at the bottom is equal to M times 3.6 G plus G. And the tension at the bottom is therefore equal to 4.6 mg. So you're adding the two g's together. So I'll move that over here. The tension at the bottom is equal to 4.6 mg. So when the object is at the bottom, it will be experiencing a tension that is 4.6 times its weight. And that is how you would solve this problem here.